Just listen for a second. The hum of your computer, maybe a bird outside, the sound of my voice. We're so surrounded by sound all the time that we barely even notice it. But have you ever really stopped to think about what sound is? What's the incredible, invisible journey it takes to get from over there all the way into your brain? Well, that's exactly the question we're going to dive into. We're going to pull back the curtain on this thing that's a fundamental part of our lives. Together, we are going to follow a single sound, from the moment it's born all the way to its final destination inside your head. It's time to make the invisible visible. So where does it all begin? Well, our journey starts right at the source. And it turns out there's one single, surprisingly simple secret behind every single sound you've ever heard. And there it is. That's the key. Without a vibration, there is no sound. Period. It is the one unbreakable rule of acoustics. Nothing in the universe can make a sound without moving, without shaking things up a little. So what do we mean by vibration? It's really just a word for a super fast wiggle, a rapid back and forth movement. Think of it like a tiny high-speed dance that gives birth to everything we can possibly hear. And once you start looking, you see this in action absolutely everywhere. You strike a tuning fork and you can literally see it blur and feel it hum. You pluck a rubber band and you see that to and fro motion creating that twang. The buzz of a bee, that's just the sound of its wings vibrating hundreds of times every second. Even my voice, the words you're hearing right now, are just my vocal cords vibrating. Okay, so we've got a vibration, but how does that wiggle travel from, say, a guitar string all the way across the room and into your ears? I mean, it doesn't just teleport, right? It's got to ride on something. And that's the thing about sound. It can't travel through nothing. It needs particles to carry its energy. We call this carrier a medium. And it could be a gas, like the air all around us, a liquid, like water, or even a solid object, like a steel beam. So how does it move? You know, the best way to picture it is like a domino effect. The vibrating object pushes on the air particles right next to it, squishing them together. That's a compression. Then, as the object moves back, it leaves a little bit of empty space with fewer particles. That's a rarefaction. This creates a chain reaction, a wave of high and low pressure that travels through the air, carrying the energy with it. And the particles themselves, they just wiggle back and forth in place.
And this leads us to that famous scientific truth made famous by Hollywood. In the vacuum of space, there are no particles. There's no medium to carry the wave. So no matter how huge the explosion, the sound literally has nowhere to go. It is perfectly, completely silent.
Now, this invisible pressure wave hits our ears, and this is where our brain works its magic. It acts like a translator. It interprets the frequency of the wave, that is, how fast the compressions arrive, as pitch. A fast, high-frequency wave sounds high-pitched, like a flute. A slow, low-frequency wave sounds low-pitched, like a tuba. And at the same time, the brain translates the wave's amplitude, how forceful those compressions are, into loudness. A small amplitude is a soft whisper, a huge amplitude is a loud bang. You know, a sound wave doesn't just travel in a straight line forever. The world is full of stuff to bump into. And when a sound wave hits an obstacle, well, that's when something really fascinating can happen. Just like light bouncing off a mirror, sound waves reflect off surfaces. We call this an echo. But what's really fascinating is the role our brain plays. It processes sound so incredibly fast that it actually merges any reflection that arrives within a tenth of a second of the original sound. So to hear a distinct echo, the reflected sound needs to be delayed by at least that long on its trip back to you. We can even calculate the exact distance needed for this. When you factor in the speed of sound and that 0.1 second processing gap in our brains, you need to be standing at least 17.2 meters away from a big wall to hear a clear echo. That's about 56 feet. Any closer and your brain just mushes the sound and its reflection together. This is a super important principle for engineers who design concert halls. And of course, we've gotten pretty clever at manipulating this reflection. A megaphone's cone shape is specifically designed to bounce the sound waves forward, focusing their energy. A stethoscope does the same thing, using reflections inside its tubes to channel the very faint sound of a heartbeat right into a doctor's ears. So far, we've pretty much just been talking about the sounds we can hear, but the world of sound is so much bigger than that. There is a whole universe of vibrations happening all around us that are completely silent to our ears. This is where sound gets its superpowers. What happens when the vibrations are just too fast or too slow for our ears to even pick them up? So take a look at this. Humans can typically hear frequencies between 20 and 20,000 hertz. That's our audible range. But a dog, its hearing extends much higher. And then you have an animal like a bat, which operates in a whole world of ultra-high frequency sound. We call it ultrasound. That is completely beyond what we can perceive. And our ability to harness this invisible sound is just incredible. In factories, we use its powerful vibrations to find tiny cracks in metal or to clean delicate electronics. In medicine, it's even more profound. It gives us the first images of an unborn child. It can shatter kidney stones without a single cut. It is a truly powerful, invisible tool. This technology is also the basis for sonar. By sending out pulses of ultrasound and then timing their echoes, ships can map the ocean floor in incredible detail. They can find everything from underwater mountains to sunken ships. It is, quite literally, seeing with sound. Okay, so we followed the vibration as it became a wave, traveled through the air, and even bounced off walls. But there is one final, crucial step in this whole journey. How does this wave of pressure become a thought, a memory, or a feeling right inside your head? This whole amazing biological machine is designed for one single purpose: to turn a physical wave into an electrical signal. The outer ear funnels the sound wave to the eardrum, making it vibrate. These vibrations get amplified by 3 tiny bones and sent to the inner ear. And it's here that the most critical part happens. The physical energy of the vibration gets turned into electrical nerve signals. Those signals are what travel to your brain, allowing it to finally perceive sound. And you know the most amazing part? This complex, multi-stage journey, from a physical wiggle to a wave in the air to an electrical signal in your head, it all happens almost instantly. It happens for every single sound you hear, all day, every single day. So, in the end, that's what every sound is. It's a story. A story that begins with a simple vibration, travels as an invisible wave of energy, and finishes as a complex electrical signal that our brain somehow decodes into meaning and music and language. It really makes you think, doesn't it? We just unpacked one of these invisible processes that shapes our reality. So what else is going on right in front of us that we just haven't learned to see yet? What other incredible journeys are waiting to be discovered?